Hello everyone, I'm Fontaine and I'm excited to share with you our work on the importance of environments in human-robot coordination. This is work with Sophie Xu, Yulun Zhang, Bryon Tjanaka, and Stefanos Nikolaidis as part of the Icarus lab at USC, and Sophie, Yulun, and myself contributed equally to this work. So if we look at human-robot interaction so far, much of the focus has been on creating models of human actions and state and incorporating those models into robot decision-making. However, environments have been studied to a lesser degree, and if changing the environment, our central thesis in this paper is changing the environment can result in significant difference between coordination behaviors. So why does this matter? Note, we each arrange our homes differently, so if environments affect coordination, we should be studying environments closely if the goal is to have robots in our homes. So we propose a framework for the automatic generation of environments that are realistic. That is, they should match a data set of environments that we're given. They should be valid. That is, they should, if we give a task to a human-robot team, it should be possible for them to solve that task, and they should be diverse with respect to coordination behaviors. And so we use as a test bed for this problem the Overcooked environment that is becoming increasingly popular to test collaboration between agents.
Hi everyone, I'm Yulun, and I will present the framework for automatic environment generation. Like Matt said, we wish to generate environments that are realistic and match human-authored environment. Therefore, we train a generative adversarial network with human-authored examples. GANs are known to be able to learn from data and generate realistic content, such as images. However, the issue with GAN-generated environments is that they are more often than not invalid. For instance, this is an example environment generated by the GAN. The environment has only onions. It does not have a pot to cook the onions or a serve point to serve the onions. Also, the agents cannot access the upper half of the environment. To make the GAN-generated environments valid, we use a mixed integer program, where we search for the environment that satisfies validity constraints with the smallest added distance. The mixed integer program acts as an editor that repairs the GAN output. We then simulate the robot and the human agents and evaluate their coordination. For instance, we evaluate how fluent the teamwork is by computing the time that the two agents acted concurrently, or the time that one agent was stuck waiting for the other agent. As we said, we wish to generate not just one environment but different environments that result in a diverse range of coordination behaviors. Therefore, we follow a quality diversity approach, where we use CMAME, a state-of-the-art quality diversity algorithm, to search the latent space of the GAN for environments that exhibit different coordination behaviors.
Hi, my name is Sophie Xu and I will present you the result of our work. So we first ran this automatic framework generation for a human and a robot agent. The robot agent solves a QMDP in real time, estimating the human subtask, while the human agent acts based on a manually specified rule-based model. Here we show two generated levels where the team fluency is very different. On the left-hand side, the environment results in high team fluency and good coordination. You can see that the key objects are distributed evenly around the environment, such that both agents have easy access and can act concurrently throughout the game. On the right-hand side is an environment with low team fluency. You can see that there are narrow corridors in the level, and one of the agents needs to wait for the other agent to finish passing before going to pick up a plate. And do keep in mind that the significance of this demonstration is that in the different environments, both agents actually run the same algorithms. So here we have observed differences in coordination of simulated agents, but what about real users? We conducted a user study where we selected low team fluency and high team fluency levels and had actual users play them along with the robot agents online. We saw that even though the robot agent ran the same algorithms, we can see that the percentages of the concurrent motion are high for high team fluency environments. In other words, the team fluency observed in simulations also translates to real-world users. And this actually concludes our results section. So this work falls into the umbrella of scenario generations for robust human-robot interactions. And besides this work, we also have here at RSS a second paper where we focus more on finding failure cases in a real-world shared autonomy setting. I hope you enjoyed this work. Thank you.